All right, so in Chapter 18, we spent some time talking about sampling distributions. What could happen when we sample? And we specifically focused on proportions. So today I want to talk about means, okay, averages. And there's an important concept you're going to read more about in your book called the central limit theorem. And I'm going to summarize it in totally not official jargon. The central limit theorem basically says the normal model works for means too. So everything we're doing with proportions, we're also going to be able to do it with means. Now, we're going to explore this a little bit more in class. I want to show you some nice visuals that might help with this idea. So here's what you need to know about the normal model. When I say it works, we do have to change it just a little bit. When we talk about sampling distributions, so now I'm taking a survey or a sample. Instead of asking a yes/no question, I'm asking a number question, quantitative data, and I'm going to get an average. So my normal model is going to be centered at that true average. View is a true average. And I do the standard deviation just a little bit different. I take the standard deviation, but I divide by the square root of the sample size. Okay, it's going to bring our normal model just a little closer together because we're sampling. All right, and just like with proportions, we can't automatically always do it. We do need to check some conditions before we use the normal model. You'll notice conditions 1 and 2 are the same. The data needs to come from a random sample, and our sample size, that's n, should be less than 10% of the total population. But our third condition is a little bit different. Last time we did NP had to be greater than 10, and Q had to be greater than or equal to 10. I can't do that this time because P is a proportion, and I'm dealing with means. So instead, your book just calls this, well, the sample needs to be large enough. Well, how big is large enough, Ms. Curtis? Generally, if you're in the 40 to 50 range, as in your sample size is 40 to 50, you're going to have no problem. We'll talk a little bit more about how big something needs to be when we explore a visual in class, as well as when we get to Unit 6. So let's go ahead and check out an example. At birth, babies average 7.8 pounds with a standard deviation of 2.1 pounds. Now, this is truth here, okay? If I could look at every baby in the universe, this is the average birth weight. So a random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of only 7.2 pounds. Is that unusually low? So our question is, babies were supposed to get an average of 7.8, but we're only getting 7.2. So is that weird? If it's weird, then maybe I can sue that factory for like polluting the air and causing the babies to be born underweight. So in order to check that out, we're first going to check our conditions. Condition number 1, do we have a random sample? Well, as a matter of fact, we do. It's said it right here, right? A random sample. So I'll just write down that it says so in the problem. All right, then I'm checking to see, is my sample less than 10% of the population? Well, I checked out 34 babies, so 34 needs to be less than 10% of, well, is it all babies in the world? No, I'm specifically looking at babies that are born to mothers living near the factory. So this may or may not be a true statement. I'm not sure. I don't know how big this town is, but I'm guessing they've probably had more than 340 babies, you know, in the past few years. So this one might be a little questionable. I think would be okay. And then 34, well, I said 40 to 50. This is pretty darn close. So we'll just say 34 is going to be a large enough sample. I know that seems a little arbitrary now. I promise I'll give you a little more information. Okay, so let's go ahead and use the normal model. We said it's going to be centered at the true mean. But this time we're going to take our standard deviation and divide by the square root of n. Okay, that's given here. It's going to be in your textbook. That's our formulas. Okay, so I have my normal model. It's centered at the true mean. Okay, check that out in the story problem. I said truth was an average of 7.8 pounds. Truth is a standard deviation of 2.1. Those are the numbers I'm using. So centered at 7.8, standard deviation is 2.1, and I divide by the square root of my sample size. I know that's a little strange. It'll take us some getting used to. And this number actually is approximately 0.36. All right, so if I go ahead and sketch out my normal model here, I'm giving myself lots of space. Okay, remember, centered at the mean, 7.8. And then I use that standard deviation number to tell me how far to go up and down my 3 standard deviations. So I did that ahead of time, so I'll just jot these down for you. Oh, my apologies. I only went up and down 2. I must have been feeling a little lazy when I wrote these numbers out. So you can go ahead and fill in the others. The reason I only went up and down 2 is because remember that 95% within here, right, is something that's not weird. Right? If I got an average of 8.16 for my baby weight, I wouldn't be worried at all. Okay? That's just some minor differences due to sampling. All right, so let's go back and revisit the problem. It said, a random sample of 34 babies born to mothers living near a large factory that may be polluting the air and water shows a mean birth weight of 7.2 pounds. Is that unusually low? 7.2. Is that weird? So hopefully you're looking for that in the normal model. Well, 7.2, that's somewhere in here. That's not weird. Oh, so these women, they can't go through the factory that their babies are being born underweight. It's not unusual. All right, so that's basically what we're going to be doing with means. Same idea, we're going to be constructing a normal model using a little bit different of a setup, and we can use that normal model to help us think critically about information and judge if something is unusual.